Okay, let us discuss what actually deep learning can do where the machine learning fails. So deep learning is a learning where you have hidden layers. In machine learning, we have input layer and output layer. In deep learning, we can have set of hidden layers in between them. Then this number of hidden layers can be termed as the depth of a machine learning, depth of the deep learning network. So it can be connected, all the neurons are connected. So deep learning is a learning where you have a number of hidden layers. Because of this hidden layers, it can represent, the representational power is exponential. It can learn the data very deeply, and it can extract the features. Remember one point in machine learning, the features are extracted manually. Machine learning, manual feature extraction. Deep learning, automated. You need not tell what is the feature. Deep learning network, it will automatically it it extract the features. Automatically it extracts the features. So it is a quite amazing thing about deep learning. It can handle more and more data. Let me show you one table where mm, yeah. So machine learning, it relies on structured labeled data for training, but deep learning can work with unstructured data, something like images, videos. It can work with audio. There is no need of structured data. In machine learning, our data was something like numbers, text, but deep learning can even recognize the handwritten characters, images, videos, audios. All these things are unstructured data. In machine learning, feature extraction is manual. You have to tell what is the feature. For example, you are classifying a dog. You should tell what are the characteristics of a dog, what are the characteristics of cat. You have to tell manually. That means you need an expertise, domain expertise to tell which is a dog and which is a cat. Whereas in deep learning, the features are automatically learned by the model from the raw data. So here already we know that machine learning algorithms are SVMs, KNN, K-means, and so on and so forth. Machine learning is effective for small and medium data sets, but deep learning can handle vast amount of data. Generally, machine learning algorithms are computationally less intensive. You can run on CPU, but whereas in deep learning, you need minimum GPU, and people are using TPUs now, tensor processing units for that. And this is very good when the data relations are linear, but here it can handle large complex relations. But one aspect of deep learning is that it is something like black box. You don't know why it was recognized as a cat. You don't have any mechanism to find out why that particular image is classified as a dog by the model. It is black box. You cannot know that. So that's why we are talking about explainability in that model. That is an issue in deep learning. But whereas in machine learning, you know that very well. So with that introduction, let me uh, let me do go back to this. Let us see one particular problem. Let us dive into one particular problem which we tried to solve in previously, and that was classification of using a perceptron. For example, what is perceptron? Perceptron is a single unit which will classify the units, the inputs, and there will be using an activation function. So something like you'll be going with a linear relation W1 x1 plus W2 x2, two inputs, plus B bias, and you will subject this to some activation function, let us say sigmoid. That is a machine learning, classic machine learning problem. So for example, you have AND gate. What is AND gate? When x1, x2 and y. When x1 is 0, x2 is 0, x1 and x2 is 0. 0 and 1, this is 0. 1 and 0, 0. 1 and 1, 1. So all the three are negative and this is positive. So when you plot a graph, 0, 0, that is negative. 0, 1, negative. 0, 1, 0, negative. 1, 1, that is only a positive. Now you can separate this data, positives and negatives, by a simple, a straight line. You can draw a straight line which clearly classifies, separates negative and positive points. Now similarly, you can do the same thing with R. What is R? Again, x1, x2 and y. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. So if you plot a graph, this is the negative point and this is positive, this is positive, this is positive. Even in this case, I can draw a straight line which will separate the positives and negatives very clearly. So we can solve this with perceptron machine learning problem. But the problem comes when we deal with another relation, exclusive OR. So in the exclusive OR, if you see the data, it will output 1 only when one of the input is 1 and another is 0. So 1, 0 is 1, 0, 1 is 1, and 1, 1 is 0. So if you want to plot this graph, 0, 0 is a negative point. and 1, 1 is a negative point. And this is a positive point. 1, 0 is a positive point. 0, 1 is a positive point. Now, you cannot get a straight line which will divide this positive and negative. No matter what orientation you take, you cannot have a single straight line separating positives and negatives. So this is where the perceptron failed, because here the data was not linearly separable. The data was not linearly separable. That means, though you may have the set of weights, but you cannot find weights which will separate these values. So now let us do one thing. Let us try to solve this XOR with a hidden layer. And let us assume the activation function as sigmoid. Let us consider a simple model. You have x1, you have x2, and you have h1, and you have h2, that is the hidden layer, and of course y, the output layer. Now let us take some values that will work. For a simple case, let us say this weight is 20 and this weight is also 20. And let us assume this weight x1 to h2 is minus 20 and this is minus 20. And the bias here is minus 10 and the here bias is plus 30 and here the bias is minus 30. We can work with any values, it will be converging, but to make it more simple, we are taking a simple values. So let us, and these values are 20 and this is also 20. So what will be the H1? H is sigmoid of bias plus W1 X1 plus W2 X2. And Y will be sigmoid of bias plus W1 H1 plus W2 H2. Now let us do this simple math. Let us x1, x2. What are these values? Firstly, it is 0, 0, 0, 1, 1, 0, and 1, 0, and 1, 1. Now let us calculate H1. What is H1? Sigmoid of W1, W1, X1. W1 is 20 and this is W2. So 20 X1 plus 20 X2 plus bias, that is, what is the bias for H1? Minus 10. So 0, 0, 20 into 0, 20 into 0, 0, minus 10 of sigmoid is anything value less than 0 is 0. 20 into 0, 20 into 0, uh, second one, 20 into 0 is 0, plus 20 into 1 is 20, 20 minus 10. So 10 plus 10, it is 1. We have in the last class, we have how the sigmoid works. Any positive value, 1. Any negative value, 0. So similarly, this will also be 1. And here it will be 20 plus 20, 40 minus 10, 30, that is equal to 1. So this is H1. And what about H2? H2 will be calculated sigmoid of minus 20 x1 minus 20 x2 plus bias 30. So 0, 0 plus 30, this will be 1. 0, 1 minus 20 plus 30 plus 10, 1 minus 20 plus 30, again 1. And when it is 1, 1, minus 20, minus 20, minus 40, minus 40 plus 30, minus 10, so it will be 0. This is H2. What about Y? Y is bias, which is minus 30, and H1 W1, that is 20 H1 plus 20 H2 minus bias minus 30. So when both are 0, this is minus 30, so the value is 0. When one is 0 and another 1, 20 minus 20 plus 30, 40. So H1 is 0 and H2 is 1. So 0, 10 minus 20 minus 30 is minus 10. Now H1 is 1, H2 is 1. 20 plus 20, 40 minus 30, so it will output 1. Then again, H1 is 1, H2 is 1. This is again 20 plus 20, 40 minus 30, 10, that is 1. Then the remaining value H1 is 1, H2 is 0, 20 minus 30, this is 0. So we got the exact answer with a deep learning layer, with one deep layer. If you see H1, it is acting as OR gate. So only 0 zeros are 0, all others are 1. And this is acting as the flip of OR, that is opposite of AND gate. AND gate will produce 1 in case of both ones and remaining values will be 0. It is opposite of that NAND gate, and this is the XOR gate. So by choosing a deep layer, we could solve. Now what we are doing in this is, we are having two hyperplanes. This is one hyperplane, this is another hyperplane. So this is how the deep XOR problem can be solved by deep learning. Here you can remember, you can talk about universal approximation theory, which says that if you can, if you have at least one hidden layer and an activation function, one hidden layer at least, and activation function like sigmoid or ReLU, then you can approximate any function to the desired accuracy. You can solve, you can predict that to any accuracy. This is known as universal approximation theorem. So here what we have done is we solved that XOR problem with hidden layer.